I think positioning system with IoT. The reason is that because when in a building with so many people walking, sometimes you may lose the direction. Sometimes you need to know where you are looking or where you are going, and therefore that is one of the motivation. And we have used a different method, and the talk is divided as follows: with introduction and a machine learning based method and a proposed system, and then with the TSK fuzzy in inference approach, one of the hybrid approach we are going to use, and with the evaluation result with both numerical computing and visualization, because some of the results being presented with visualization will be much more interesting to especially participants who do not have the idea about this project. So the reason why we use indoor positioning system, as I mentioned, we use a tracking system. First of all, we use that for lots of objects, but now with also people, and then to locate themselves, and also to know the direction. Because these days people use a lot of smartphones. They don't want to ask people with the direction, but also it helps, especially when you have lots of goods and devices you want to send to the destination. You do not want to take a lot of time to find where you are going and where you are up to before you reach the destination. Then, especially it's used in smart buildings and smart environments, and lots of smart buildings has been installed with a lot of sensors. So IoT is the one that to help. But also inside the building, GPS cannot work well. As we have known, GPS usually works outside the building, and therefore we can integrate the Wi-Fi, Bluetooth together with IoT, and that will deliver a very useful example. And as you know that for those smart buildings, the indoor navigation path planning for for self-driving cars. So it means that the self-driving car will move from one place to another. Sometimes it's also helpful for the warehouse inside the Amazon warehouse, that it can be like as large as like 5 football grounds, or even like at least like one football ground, such a huge space. Then you need the machines to do the transportation itself. Therefore, the indoor positioning and navigation system is very helpful. So it will find the shortest path in real time. And to find the shortest path, it's not easy, because when you have some objects that become the obstruction, especially in warehouse, and then sometimes the routes will be changed, and sometimes the routes that the system identified yesterday is not the same as today. That the hospital is also helpful, because a lot of patients, especially those older patients, they are not mobile enough. Therefore, they need the tracking system to help them, or at least the nurses who are new to the place, who are not familiar with the hospital, they can bring the patients easily. And that is why the indoor positioning system will be very helpful. And especially now as you see the picture, lots of people are using a smartphone to use. So I want to talk about the basic backgrounds that other people have used. So one of the methods called trilateration method. So which means that you're using X, Y, Z as the position, as you can see the circles. So you may have 3 of the reference points, and then each of them is calculate. Then the joining part of all the 3 reference points will be the position of the place or the object. And in this case, this is also possible in 3-dimension background, that you then can look at the X, Y, Z or X, Y, Z direction. Then the challenge is that if the object moves too fast, and the way that you track it is not good enough, and therefore it has a kind of measuring received signal strength indicator. However, that depends on the place. If you can have a strong signal, and also with a very fast wireless broadband, such as the use of 5G, then that's possible. But if the object, as I say, if the object moves too fast, or with the people, nowadays we are locating the place for the people, then you cannot do this very accurately. And therefore, you may even lose track. The positioning you have maybe seconds ago, or worse, even minutes ago. And that is how the machine learning based method has been used. So machine learning method that has been used in all the inputs, Bluetooth signal and Wi-Fi signal. So then we have the input layer to train, and at least the system is smart enough to be able to track things much better. And then we give a lot of pre-deployed beacon devices in the form of training data sets. So training data sets is not just on the computer systems, but also on signal and communication systems. Then the ML predicts the corresponding location, because the thing is, if the people or the object move too fast, then we cannot actually track them good enough with a significant time gap. And with the use of machine learning, we can significantly reduce the time gap. And then we then have a hidden layer and the upper layer. And this is the simple concept as it is. And then having said that, when we are doing implementation, it's not as easy we hope for, because we have to get a training data set and then we customize it, because sometimes the training in a theoretical situation are not the same as in real life. So we may have to adjust. For instance, if let's say you work in some environment and if the object is fast, then you have to fine tune there. And there is a stage of fine tuning. And then we then test it better. Then after that, we can have a better predictive outcomes. But having said that, it's always not easy, because we have to also track with the three, similar to what you have seen with 3 dimensions, X, Y, Z. And then, so we will also help us to get a better outcome. So another issue, if we use machine learning, as you know, data set become very important. AI and data science have worked together. So there are issues of not having enough data if you are only testing with just single or a few objects or a few test scenarios. Therefore, we need usually to simulate with enough data or enough people, enough project in order to make the machine learning algorithm. So therefore, we will have to ensure there's sufficient data set in order to test, or even we do a real life test with several people working in a story, in a building, and then we see whether it works and whether it's accurate enough. So our proposed system is as follows, and I will just go through them again with the training phase, the rule phase, and the testing phase, because there's a gap between the theory and the practical aspect. Therefore, the rule base will help us to ensure we match better to the scenario. Of course, the scenario can be adapted based on the change of circumstances or the change of demands. Then with the training data set, first of all, we have the data preprocessing. Then we have a clustering. Then we use the TSK fuzzy rule extraction. I'm going to go into some details later. Yeah. So now I'm just giving an overview. Then with the rule base will help us to adapt better. Then with the testing phase, then we again perform the test to ensure that we get the preprocessing and the TSK fuzzy inference and the predictor label. And even so, we also get no very accurate result. I'm going to show by this that will help us to locate the location, the object or the people better. So that is the summary of the proposed system. So there are a lot of theories and even mathematical formulas, like about 10 mathematical formulas, but I'm going to not to explain them, but I'm just to explain the overview, the TSK style rule base, why we have to use, because as I've said, the sparse data set, you may not get enough the feature selection. Therefore, feature selection are used to enhance and to normalize using another method. So we use another minimum maximum method to reduce the dimensionality of the given data set. So at least we find what's the minimum and the maximum requirement, and then we find to bridge the gap, and then to calculate the k-means clustering system. So at least we know how to group them together with a similar behavior. Of course, there's some objects, some people, they move in a certain similar behavior, especially in warehouse. It's much easier to understand because robots only walk in certain directions, or maybe like there are also some systems they have more predictable movement. So in a way that we can calculate them better. So each cluster is expressed as a TSK rule. So back from the practical aspect, then we then make them as a rule. The rule is not just invented out of blue. It's invented based on the 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 systems and the demands, then we fine tune, and the system combines all the rules and generate into the final rule. So then we check the validity of the rule, and we compare with the optimum number of the clusters determination. So that we then compare with another method, because another method called elbow method, they calculate the ultimate k-means. So it's like different method that try to do different thing. But in another method, what they find is that they try to focus on k-means, and they find the turning point, which means that the change of circumstances is the thing like, okay. So change of circumstances means that if I'm in position A, then I move to position B. So this is the change of circumstances. In the theory is called turning point, k-value turning point. Okay, so just not to make into very theoretical thing. So this is how it is in reality. You are here. By the time the system analyzes, maybe the object already moved. So there's a significant time gap. So the K cluster means to calculate the medium so that it can then predict what's happening. If let's say you can find like this object like move here to 5 seconds, then 5 seconds later maybe there. So the input should be at the early stage or almost towards the end of the object or the people going to move. Yeah, and then of course the issue is that if you input you get it too late, you are not going to get it. So you have let's say in order to do the test properly, you may have to measure how fast people walk. For instance, like you may have to go to the hospital, like patient, they walk very slowly. Like maybe 2 seconds for one step, and then then you can then fine tune that. But then if you are measuring athletics, they are too fast, and you may have to fine tune 1 second for 5 or 10 steps. So you have to fine tune the measurement and the input value. Then, and of course there are rules. So mathematically, we then transform into algorithms. So it's like this is the condition, X is A and X2 is A, and then therefore we have to calculate whether they are in the right range. So then we have to set the rules to find, first of all, are they in the right range? Secondly, is the system capable to catch? Because if the system is not able to catch, then it's no use. It's similar to, we see a lot of people that can run fast, but when our eyes can catch the fast movement, but our body cannot, so we have to coordinate whether the system is able to catch, and we have to also adapt and fine tune and optimize the system in order to catch the required pace. So that this is called firing strength. Firing strength is to ensure all the rules. So we check all the rules are very applicable to the real life measurement. And then we then measure starting from 0, because you have input 0, and then after that you will get an output 1 that's the closest. But normally in real life it's very hard to get it. You will get like as low as 0.2 something and as high as 0.7 something. And this is in a nutshell. So there are also other rules. So this project is very mathematical based, but we try to bring the theoretical contribution to the real world solution. So there are also 2 very important formulas for us to follow with the TSK fuzzy interpolation and curvature-based feature selection because of the time constraint. Just sum up as like there are 3 steps to match the degree determination to find the k value, and then we firing degree calculation to double check with the rules, and then the rules will then calculate the key values, then subsequent sequence integration, then integrate all different values together to identify the predicted movement or position, then the curvature-based feature system to have a 2D data reconstruction. We understand how it works, the feature weight calculation, and then we then calculate and predict the movement. And after that, feature ranking and selection means that we rank all different selections, and then we pick the most or the highest value. So the feature selection aims to select the most relevant attributes or the highest values, and then curvature-based CFS method to rank the weight. So we have to calculate them and rank them accordingly. And then this is how it works. Like we have all these, we have all the sequences, we then measure them, then we have the values with the A's and B's. So A's original, B's is the predicted. Then after that, we then do the transformation and the normalization. And after that, we then have the fuzzy logic calculation. And we sum up all the values as the weightage. And then as a result, then we then get this final value. And the final value will then determine the position. But then because of the time constraint, with the data set of 2016, we used a very comprehensive data set with 1,540 instances and 21 classes and 65 attributes. We have those values, then we measure at different places and positions, and then this is the value that we've seen. So this is a baseline. If we pass the baseline, it means that at least we meet the minimum requirement. But if not up to the baseline, it means that there's something not right. It might be because the signal is not strong enough, or might be because of the location of the building. You've got very thick walls, or maybe the location is far inside of the building. So therefore, we have different measurement. And I'm going to show you the visualization aspect. So this is the actual simulation we do. So we actually measure in a building with only 3 floors from ground, first and second floor. This is the appearance of how it look like, and these are the the places you can visit, but there are some empty places you cannot, maybe like because of the empty space or something. So then this is the scenario we go into. So we then can see they have different values corresponding to the accuracy and the validity of the results. And also in the first floor, north corridor. So we noticed that in the first floor, there are some places they have a very good result and some places are not. So it then show with the different colors. Sorry, you may not see that very clearly because it's a very tiny image. And then we have the second floor, north corridor. And in some places, you get good results, some are not. Then similarly on the ground floor, some you can see well, some you can't. And similarly, we then try to test at different places in the lab, and we have very different outcomes. As you can see, it will give you very different scenario. And also then we double check with the first scenario, because sometimes you may not get the result. You want to double check, and we then validate that certain places we can see well, and then we then have to figure why in some places we cannot get the outcomes we are expecting. So just to sum up with everything, the testing accuracy, as you can see, C8, C9, C10, they corresponds to different data instances. So in some we do well, some we don't. As you may have seen the previous slide, this is also the case. There is also how it's interesting to find why some places we can predict better, some places we can't. It might be because of the construction of building, or it might be because like you may have to install another access center for IoT or something, or might be there are too many people working, or like too many objects moving in some places. Like in some places there are too many objects moving and you cannot track them well. There can be various reasons. So the feature selection with the curvature-based feature selection helps us, and the result get the features has been selected. At least that we pick up all the important points, but the accuracy maybe because of those reasons I've said. Then with the training data, we then train again, because failures, there's an idiom from our culture: failures are the mother of success. Once you fail, you don't feel upset. You try again. You try to improve, and you make your model better. But as you again, there are some places we don't do well. It might be because, as I've said, too many people or object move in and out, and the system is not good enough to catch. Or it might be because of the structure of building, or maybe the places are far inside the building. It's not measuring well. So the overall accuracy is only passing 50+%. There are more to be done. So the conclusion is that we have a proposal system with an IoT based location tracking system, and we at least try to integrate 2 different methods together, and we try to make the theories and practices, and then we move towards the challenging task and evaluate the real world IoT devices. And you can say to my group members, we're working in different universities. So if any question, please let me know. Thank you.